Okay, folks, I still see some people trickling in, so we'll give them 20 seconds. 20 seconds.
You're saying that to the wrong audience.
Yeah. Fair enough. All right. Hopefully you got some food, some sugar, some caffeine, sunshine. I was telling Arvind this is the toughest slot. This is the post-lunch slump, so be prepared for 10 minutes of stand-up from Arvind here. We're on to direct air capture. I'm going to introduce our session chair, Dr. Arvind Rajendran. He's a professor of chemical engineering at the University of Alberta. Within CanCO2Re, his work supports the assessment of direct air capture technologies for Canadian climate. Thank you.
Thank you. Thanks, Carson. You really know your friends by when they schedule your talk. Right? So I know Carson, so I even offered a ride from Edmonton, and this is what Carson does to me. So good afternoon, everyone, and my name is Arvind Rajendran. I'm a professor of chemical engineering at the University of Alberta. It's indeed a pleasure and an honor both to be part of the project CanCO2Re and also to be here at the U of C, where we have had many collaborations, including the ones that we have now. I'm also additionally very happy to introduce Evelyn Forbes, who is going to speak to you about what we are doing at the U of A, and also Navjot Sandhu. Navjot she will magically appear, and she's going to blow you off with her talk. And it's particularly, I'm happy because Navjot did her master's at the U of A. So welcome, and this is an interesting group. We have to talk about all the engineering data that we collect and try to put it in context to this really eclectic group that goes all the way up to policy. So we're going to try and do our best, and we'll see where we get. Okay. So this is the agenda. So I'll probably give you a bit of an introduction and a context setting, and then I'll give the floor to Evelyn, after which we'll have Sean, who steps in for Malte, and then finally we'll hear from people that are actually doing it on the ground, and this is Navjot. So this is a standard introductory slide that is, I think, essential, and also it actually puts us in perspective. To ask, okay, why is DAC difficult? I teach separation processes for a living, and this is very, very helpful. So what we are trying to do is really pick needles from a haystack, and that costs you both energy and that costs you both volume, right? So these are the two things that contribute to this. So this is a classic Sherwood plot, and I will show you this one here. So I've plotted this as inverse feed composition. So essentially, the feed composition increases as you go from right to the left. It's kind of inverted. And then on the y-axis, you have what is called as a minimum thermodynamic energy in order to perform a separation. So the way you can think of that is if God were to do a separation, that is really what God would need. Even God cannot do that for free, because that is how they set up thermodynamics, right? So, and that is the most important thing for us to realize, but it also tells you that if you're here at 400 ppm, if you do the ideal separation, it turns out to be about 0.5 megajoules per kilogram. And if you look at some of the estimates of what the DAC energy costs are, they are somewhere in the range of 10 to 15. We can debate about these, but they are somewhere there. But that tells you that the efficiency with which we can do these processes is really about 3 to 5% efficiency. So it is not just you get a double whammy. You have to spend energy into concentrating, but you also are fighting against efficiency. So the other thing that you talk to DAC developers, they'll also tell you that it is not as bad as the way thermodynamics is set up, because if I look at 4%, that is really NGCC flue gas, and if I go from 4% to 400 ppm, that's about 100 times leaner, you only get a 3 times improvement in energy. So you actually can do this without wasting too much energy. And that is also reflected here in the famous Sherwood plot, which gives you, again, the concentration in the same axis as here against the cost of performing a separation. And this line indicates where we are with a DAC. And as you can see here, you're somewhere in the range of about 2 to thousands of dollars per kilogram. I think if you look at the current DAC prices, they are probably about $1 per kilogram, so about $1,000 a ton. That's reasonable. So two things. One, you get slammed by energy because you have to sit there and pick CO2 molecules from a whole bunch of air. And you also have to treat all of that in order to concentrate your CO2. And that's really where a DAC becomes increasingly challenging. If you look at industrial DAC technologies, I can talk about at least two that are more or less scaled up. And I think we have colleagues from both of these companies here in the audience. The first one is Climeworks, and this is a Swiss company. They use solid materials in order to perform the separation. They have two plants with, I insist this is a design capacity. One is Orca, which is 3,600. The other one is about 36,000 tons per year. And they've had some challenges, which they have actually been very open about. And the other one is what Navjot is going to talk to you about. I'll leave her to take you through this. This is what used to be Carbon Engineering, now with Oxy. And they're building this almost a 500,000 ton per year plant. I think half of it is about to come online soon. We'll probably hear from Navjot. And interestingly, a lot of this has origins here at the U of C, so it's indeed nice to come back here. Well, if you look at DAC costs, so this is a plot that comes from the US Department of Energy. I think it came out a couple of years ago. If you look at where our DAC costs, they're all over the place, right? And it's not just the cost, but also implementing it on the field has been a big challenge. And for those of you who have followed this debate, in the last months, there's been a lot more talk about essentially a piece that came out from an Icelandic newspaper, which spoke about the challenges that Climeworks has faced in order to scale this up. And in fact, Climeworks has spoken about this almost a year ago regarding the challenges that they're facing. So there is just the science, and then there is engineering. So they are both equally challenging. So I'll take a few minutes to talk about the first one, which is solid-based systems. And I'll let Navjot later on take over the next half. So this is really thanks to Mission Innovation and NRCan. So I think we really were the second tag on to this project when Sean and the colleagues realized that if they have to do TEA and LCA, they need good engineering data. And that is how we got roped into this very interesting project. And when we started this project, the real knowledge gaps were the following, right? So if you look at solid sorbents, these materials and processes are new. We have done solid-based separations for a very, very long time. But when you apply this to these kind of conditions in the way that the kind of materials that you use and the kind of regenerations that you use, this is new. These processes have not gone up to this scale until recently. And secondly, you will find that there are hundreds of papers with new materials, but very few with actually good data. So you end up with the same problem of having to deal with data in this. What surprises me is that there is little to almost no demonstration of a process in the open literature. I cannot go and look for, at this point I was hoping that I'll get 10 papers that show that you can do DAC, but you actually don't find a lot of them at that scale. There's a lot of work on materials, but very few that take it to the process level. That's where we wanted to step in and understand. So the objectives for this project was that we want to get reliable data, and this is what Evelyn is going to talk to you about, and then take that data, design, demonstrate, at least benchmark DAC processes and show that at scale, and using that, provide data to Sean and colleagues to do the LCA and TA. So this is eventually where we want to get to. So this is the techno-economic and life cycle analysis that Sean and Malte would do. And the way that we want to structure this is we want to start with sorbent characterization. So this is Evelyn and Bhupesh. And we want to go from there to here. And we have two parallel paths. So one is after we characterize the sorbents, we want to do process modeling, optimization, provide information. But without having to wait for those models, already start doing some process level experiments so that we can understand what essentially you have to model. And you can start doing that interaction and provide more refined data to Sean and Malte. So there are two main sorbents, as you can think of. So these are solid materials that have hundreds, if not thousands, of square meters per gram. So these are fizzy sorbents. Fizzy sorbents, and again, U of C has incredibly good programs in fizzy sorbents. You can talk to Travis, and there is also a session tomorrow with George Shimizu. And this is essentially a solid which can attract a gas, right? On the other hand, most of the DAC sorbents have these tethers, which are amine tethers that are stuck onto this, which essentially help you with the low concentration capture. So what happens if I throw some CO2 molecules in it? A few of them will go and sit on the sorbent because they have an attractive potential. They sit on this. This is mostly physical attraction. So that is what really takes the fizzy sorbents. And if you look at chemisorbents, your CO2 molecule can stick on the amines, which is the reactive, and there is also a physical basis. So very often you do not know how much is what. And then the real challenge is you throw water in, right? If you throw water in, the situation gets really complex. And that is really where I think the complexity of any solid-based sorbents ends up to be. And that's really what happens, right? So you don't know what happens when in these two cases. Why? Because if you look at a physisorbent, CO2 and water will fight to occupy a site. And if you look at a chemisorbent, they actually work together. And this makes very difficult to actually predict what happens and even sometimes to measure. So when we started, we said, okay, the expectation was that the DAC is a CO2 removal problem, and very quickly you realize that it is actually a water removal problem and moving air through your contactors. So we had to completely change the way that we have to look at these characterization and focus a lot more on understanding water. I think that is the greatest challenge in any of these separations is understanding and handling water. It's not CO2, it's easier. It's not easy, but it's easier, okay? So this is the kind of experiments that we want to build. So as you can see here, we try to map what is it that you want to measure at the fundamental level to what it means to different process level outcomes. And this is the matrix that we would like to build. And the highs are the ones that we want to target early on, and the mediums are the ones that we want to go later. But this already gives you the level of complexity that you would need in order to build reliable engineering models. With that, I'll give the stage to Evelyn.
Okay, hi everyone. I'll come over here. So my name's Evelyn Forbes. I'm a master's student in Arvind's group. And I'm just going to go through the work that I've been doing recently. And it's basically all experimental work on material characterization and process demonstration for DAC. I'd just like to give a quick thanks to some of our funding from TotalEnergies, CanCO2Re, and MyTax. Okay, so to start us off, we needed to choose a benchmark sorbent material for us to develop basically our systems that we were going to test materials on. And so with that being said, we did choose this Luitit VP1065. It's a prevalent candidate DAC material, which is studied in literature. It's a commercial amine functionalized ion exchange resin that's produced by Lanxess for water purification and acid gas removal. But although it's studied in literature, we actually have found that there is both inter and intra-batch variability. And what I mean by this is different batches will have different CO2 capacities, and also depending on the particle size, as you can see in this figure here, there is a whole bunch of different particle sizes, and each of those also have a different CO2 capacity. So to try to make everything fair and to make our comparisons basically across different of our systems to be consistent, we've chosen a particle size. So all the information I'll show you is for a particle size cut of 600 to 850 micrometers. Okay, with that being said, we're going to start with sorbent characterization, and then later in the talk I'll move to the process experiments. So we have the first part that I'll talk to you about is the unary material characterization that we've done. And we have 4 instruments in the lab, 2 that can give us CO2 isotherms, so that's just talking about how much CO2 absorbs onto the material, and then we have 2 that give us basically our water isotherms. And these are like all not gas mixtures, like it's simply just if CO2 is present or just if water is present. So this is work that Bhupesh has done, and so here on the left, these different plots are the isotherms, and they're at different temperatures. So it's just saying how the basically loading on the material for the gas changes with different pressures. So at different, and then each of these is a different temperature, and you can see at 400 ppm, we're down on this line right here. And on the right, you can see that this is our work on Luitit compared to other people's work. And this is where you can see that basically variation in the batches. And then these are the unary water isotherms. So they're plotted again as basically the amount of water that's loaded onto the sorbent material as a function of relative humidity. And then these ones are basically compared with another person in literature. And you can see the water is slightly closer than our CO2 was. But the big issue, as Arvind has pointed out, is that we need to know when you send in CO2 and water together, so air, how are these materials going to interact? So what is going to be the component loading, the CO2 loading and the water loading, when they're both competing or cooperating for the same spaces? And I'd just like to point out Jim Sawada. He is instrumental in building all of our binary material characterization equipment. And as well, I'd like to highlight that this is the new instrument that we built that can handle 400 ppm and a range of relative humidities, which allow us to study DAC conditions. Okay, so with that being said, I'm going to give you a brief overview of what these dynamic column breakthrough systems are. So how we get basically one of these little measurements, so one of the points on our isotherm, is we look at how if you send a step input of concentration into a column, how that comes out in the outlet. And what comes out in the outlet, the shaded region here, is actually, if you do some math to it, it gives you the equilibrium loading on this graph here. And then we can also do the desorption. So that's when you, let's say, start from 400 ppm and send in a step input of 0 ppm of CO2. And then you can watch how the CO2 leaves the column. And again, this will be like 400 ppm to 0, and this shaded area will get you, again, your equilibrium loading here. And why this technique is important is because it's the one that lets us get the CO2 and the water loadings separate from one another with not making any basically drastic assumptions, unlike other techniques like gravimetry. Okay, so this is just a schematic of the DAC DCB. I'm going to break it down into 3 main systems. Basically on this left side here, this is how we blend our gas. So it's how we get the 400 ppm of CO2, and then we can put it through a saturator to control the RH. Then here is our bed where the sorbent material that we're studying is loaded, and then we have a detector array. I'll say what makes this system special is the fact that the saturator is inside a thermostated oven, which means we can control the relative humidity quite well. We can make sure that we can get to that 95 to close to 100% RH at the different temperatures we want to study. And then the other thing that's very important about this instrument is our detector train. It is very hard when you're trying to measure very dilute concentrations of CO2 for your detector to not be affected by your water. So this methanizer and FID combo lets us see down to, I'll show you, about 0.1 ppm. So this is what the instrument actually looks like. And again, mixing station, and then inside the oven, which you can't really see unfortunately from this photo, you'll have your saturator, then your bed, and then your outlet detectors. So our detection range is from 0.1 to 2000 ppm of CO2. So DAC falls well within this range. We can do RHs between 0 and maybe even a little bit higher than 95%, between 30 and 90 degrees C. Our flow rates are typically at 50 SCCM, and our bed size is between 50 and 200 milligrams of material. And I'd just like to point out that this system would not have happened if we didn't have the funding from Mission Innovation, NRCan, and Total Energies. Okay. So what does this give us? So as I showed before, there were the different adsorption breakthroughs. And now this is actual experimental data that we have run. And we've run from 1 ppm breakthrough to 2000 to cover the full range. And what you can get, again, from the areas behind these curves is our loading. So this is basically a unary CO2 isotherm. And the reason why we did this first without adding the complexity of the binary is we wanted to make sure that we have commissioned the instrument well and that it matches up with other techniques. So this is the red squares here are basically our unary points from our DAC DCB, the new instrument, in comparison with a kind of standard ASAP, which uses volumetry. And what you can see is we have very good agreement. So we're very confident with basically our system. So, and we can quantify loadings down to 1 ppm, which means that our outlet detectors are both stable and extremely sensitive in comparison to a lot of stuff that's on the market right now. Okay, so this is now when we start looking at the binary CO2 and binary water. And these are the water breakthroughs of the bed, and then the CO2 comes out much later. And what we can see here is basically you increase the RH, the water takes longer to come out of the material, so that makes sense. But what's interesting is this is basically CO2 at 400 ppm plotted, and then these are all the different RHs that we studied at 400 ppm. And what we notice is as we increase the RH, it takes longer and longer for the CO2 to actually come out of the column. This shows that we're actually increasing the capacity of CO2 on this sorbent material, and it is quite drastic. If you look at the time frames, these are very long experiments. The adsorption alone takes roughly 10 hours for basically the 95% RH, but you can see is that we're actually increasing the CO2 capacity as we increase our RH, which is very important to understand. So we only have 400 ppm of CO2 in comparison to, let's say, the 3% of water at 30 degrees C at 95% RH, but we actually do see an effect of that 400 ppm CO2 on the water adsorption. So as you can see here, my plots in the dashed lines are the unary profiles, so that's just water, no CO2. And then we ran the same experiments in the binary profiles, and that's basically the whatever percent RH in the presence of 400 ppm CO2. And what you notice is the area between the unary and the binary curves are different, which also states or shows that we actually have an effect. So CO2, the 400 ppm CO2, influences the water breakthrough and loading. So just to kind of summarize the same thing, we can see CO2 loading plotted on the left, water loading plotted on the right. It's all at 400 ppm, and then the different RHs we ran are along here. And what we can see is that the CO2 loading linearly increases with RH, and it doubles the capacity at 95% RH. And you can also see the lift between the unary water to the binary water as well. So with that being said, the main conclusions from the DAC-DCB work is that we can quantify both CO2 and water adsorption. The CO2 capacity doubles from 0 to 95% RH, and the change in water is also proportional to the excess CO2 loading. So if we add basically 1 millimole of CO2 on, we add 2 millimoles of water on. The future work will just to complete the experimental matrix, to then model the CO2 and water interactions, and then extract the kinetic information from the breakthrough curves. Okay, so now that we've done our sorbent characterization, unary and binary, we're going to move on to our process experiments that we have run. And with that being said, we have also built a new system for this project that we can run candidate DAC process cycles on. And again, we would like to thank Jim Sawada from our lab. He was instrumental in building this instrument as well. So this is a process, again, overview of how the PDU works. We again have our mixing station here. We have a saturator that would let us study the effect of the inlet humidity on the process. We have our bed, which we're currently using about 25 grams of fluotit, and we have 3 different thermocouples that let us look at how the temperature fronts move through the bed. In addition, these are probably the heart and soul of this instrument. So we have our steam generator here. It is instrumental in being able to basically meter steam well, and we've had to build an in-house steam generator because the commercial products that we've tried have not been able to do the job. Because we want to study a range of steam flows, which means you need to be able to look at very low and high steam flows without basically having two-phase flow, which is quite difficult to do. And then the other thing is our mass spec. So we need a detector, because we're using steam as a regeneration, we need a detector that can see CO2 in the presence of steam. This is unique to the mass spec. We have not found another basically outlet detector that can outcompete it, unfortunately, at this time, because they are quite expensive. So we also have our outlet flow sensor, and this just lets us close the mass balance and to determine how much CO2 and water are coming off the bed, and then we just go to vent. Okay, so this is what it looks like. It's not the prettiest thing you've probably ever seen, but here's the mass spec. We have our steam generator here. Our column oven with the bed is inside here. And then we have our gas mixing station, which is kind of behind, so it's a little hard to see, and the feed humidifier on the right side. and then this is our switching valve right here. And so the range of operation that we can currently do is an inlet feed concentration between 20 ppm and 100% oh, sorry, ooh, can I go back? Okay, 100% of CO2 dry. What I will note is that the mass spec, unlike our FID methanizer that I previously talked about, we found it has a baseline at the sampling frequency that we can do, or we need, of about 20 ppm. So we can't really see anything below 20 ppm, so that's the one thing that the micro DCB that I showed before is much more sensitive to at its like 0.1 ppm range. The RH that we can currently handle is between 0 and 50% on our inlet. We can do these different feed flows, steam flows, and then it can handle a bed size anywhere between about 5 and 100 grams currently. And then I'd again like to thank Mission Innovation, NRCan, and Total Energies for the funding to build this instrument and to buy that. Okay, so this is our current DAC PDU cycle. So what happens is we come in with nitrogen and CO2. We're currently looking at dry inlet feed. And then our bed is thermostated to 30 degrees C in the oven. And what comes out is nitrogen at first, and then when the bed starts to saturate, CO2 comes out next until it reaches 400 ppm, and then we call absorption over. And then we start this external heating step. And why we need to do this is because we have outlet detectors in the oven, and we can't have steam condensing in them, or else we can't basically figure out what our flows are because they'll just kind of die. So this is a current necessary step. So we basically externally heat the bed with the oven until it's 105 degrees C, and we blind the inlet. And we have a little bit of exhaust gas that leaves that's the nitrogen and CO2 mixture, but it's really not significant, which I'll show you later. And then we come in, once the bed has reached 105, we come in with steam at 105 degrees, and this is our steam desorption step. The oven is still on, trying to keep it at 105, and then we'll get nitrogen and CO2 out to start, then we kind of get some CO2, and then our steam will eventually break through on the outlet. Okay, so these are the signals, the lovely signals that I get to deal with on a daily basis. So this is, I'll kind of go through it with you. So the first, this top part of the graph here is what our outlet flow sensor is reading. Then this middle part here is what the middle thermocouple in our bed is reading. And then this bottom here is the outlet concentrations that we're getting. In our adsorption step, our flow is not changing, it's just staying because we're only absorbing 400 ppm. We have a little bit of a CO2 exotherm, so when the CO2 absorbs, it releases a little bit of heat, which you can see here. And then this is our breakthrough. So the adsorption breakthrough that I've shown you a couple times now, this is the CO2 breakthrough in our adsorption step. Then we have our external heating step. You can't see the outlet flow, it's right there, but it's basically reads 0, so we kind of ignore it currently. And then we have our temperature profile here. You can see it coming up to the 105 degrees C. And then our concentration profiles are just moving around as we're losing a little bit of gas to the exhaust, and the mass spec also sucks a little bit of gas in, so we're seeing some actually oxygen encroach into the mass spec system, but that kind of proves to you how slow or how little gas is coming out if it's taking 1 mil a minute and we're actually seeing it come out. And then our final step is our steam desorption. And so what we can see here from these plots is that we have this intermediate stage where the steam's absorbing on, so our outlet flow isn't basically its maximum because the steam is absorbing onto the solid. We see in the temperature profile the steam adsorption exotherm. And then here in the composition, this is what's really, really interesting and what we study kind of, I would say, the most. So we have CO2 in red, nitrogen in blue, nitrogen in purple, water in blue, and oxygen in green. As you can see here, when the steam starts to come in, the oxygen goes to 0. The nitrogen really doesn't last for that long, and then the steam hasn't yet started to break through, which means we actually are getting some pure, dry CO2, which is not typically what I was expecting. I was expecting to see kind of all the CO2 to come out with either nitrogen or steam, but we actually get pure, dry CO2. Then the steam starts to break through, and this CO2 comes out with steam for the rest of the way. So, but what's interesting to note is that by the time you get to about here, we've reached 99% CO2 recovery, of the adsorption step, and we're sitting at about 98% purity. And if you take your flow profiles and your composition profiles and put them together, and on the left side, that's what the CO2, nitrogen, water, and total outlet flow were plotted on, you can actually see the same thing that you see in the composition profile, but with flow as well. So the CO2 is basically making up almost the entire outlet flow until the water breaks through, and that's when you start to see the water is basically reaching the total outlet flow. And then on the right axis, we've plotted the cumulative steam in versus the CO2 basically that we're getting out, and that gives us an idea of how much steam we need in per kilogram of CO2 we want to produce. And currently, if you look at the minima point, that's about 2.33 kilograms of steam per kilogram of CO2, or 6 megajoules of kilogram of CO2. And this is an unoptimized process, as we have not looked at what the optimal steam flow is. So that's what we're getting, but if you change the steam flows, this number will change as well. So in conclusion, and our future work, so the DAC PDU can quantify key performance indicators. CO2 purities of over 95%, sitting at about 98, can be reached without the use of a vacuum. At the minimum steam ratio point, so the point that I mentioned here, we're getting about 70% of the adsorbed CO2 is recovered at that point. And then, so this basically means that it's kind of diminishing returns if you think of it in terms of steam. You'll get the extra 30% of CO2, but it's not fully worth it if you're just looking at it from a steam perspective. And then our future work will be to study the effect of inlet feed humidity, to build and validate our full process models, and then basically to develop process solutions to avoid oxidative degradation, which is also a very big problem for DAC and amines. Okay, thank you so much for your time.
Well, thanks, Evelyn. The challenges of supervising good master students, graduate students, is they show you a beautiful picture of an instrument and says, this is not pretty. Come on, it's beautiful. So, Evelyn. Next, we have Sean. Sean is going to talk about how climate is going to affect DAC processes, and this is the work that he did with Malte.
And Arvind, too. So let's see. Perfect. So I am going to be presenting today about how ambient conditions affect adsorption-based direct air capture. So basically saying, when we have all these materials that we're looking at, if we actually start putting them in the real world, exposing them to real weather, what happens? And as we're going to hear in a second, this is the work of Molt Glasser, who's online, so I'm very nervous. He might be taking notes and giving them to me later. But yeah, I hope it goes well. So a few years ago, we started asking the question of what happens if you take this DAC process and put it into the real world, whether it be a liquid sorbent or a solid sorbent. And the reason we started asking this question was because this is, as we've seen, it's sort of chemical engineering. And in chemical engineering applications, you'd put one of these separation processes inside a plant, and you'd run it at a very constant sort of setup. Constant temperature, try to run it as constant pressure. You want everything to be steady state. If you're an engineer, steady state's great, right? But the reality is DAC systems are exposed to climate and weather, right? So longer term variations in temperature, relative humidity, and then very short term changes, be the weather. And so we set out to ask the question, how does this affect their performance, and how does this affect the choice of the material you'd use in a DAC system? And so this work that I'm presenting, as I said, is led by Molt Glasser and Professor Arvind Rajendran. Arvind helped out by helping us a lot with the modeling and joining us as an author on this work. And of course, I was also involved. And so we're going to look through this in several parts. So first, we're going to start out, talk about the problem specifically, how we set up a model to deal with that, how we set about optimizing, the case studies, and then some results. And so I'll talk about two pieces here. We'll talk more about the modeling and then sort of optimization and results. Okay. So first, what we needed to do is formulate a simplified steam-assisted TVSA, temperature vacuum swing adsorption system for DAC, and that could handle different sorbent materials. And so we set out to answer this question. Can we model a DAX system assuming a well-mixed reactor without spatial gradients. And what does that mean? I'll tell you again in a bit in a second, but the reactor we just saw in Evelyn's slides, if you put gas in, you saw this change over the length of the bed, right, at any given time. We're going to ignore that and see if we can get a model that works for DAC. And the reason we want to do this is the state of our sort of 1D models, and this is a model that has to, when we have temporal and spatial resolution, means we have to solve partial differential equations. Does anyone in here like solving partial differential equations? Okay, some really weird people do, okay. I won't judge you. But the point is, it's sort of hard, but it's more importantly, computationally expensive to do this, okay? So if we wanted to try to figure out how a DAC system ran every place on the planet for 8,760 hours for every year over a long period of time, it might be very difficult to do that. And so that's how you'd end up modeling it. You basically model slices of this bed and what's happening in each slice of the bed over time. What we wanted to do is use a 0D model. And by 0D model, we're saying there is no spatial resolution. This is an ordinary differential equation system. So more people would put up their hands now, I'm sure, if I asked. It's a little bit simpler and easier to solve, right? But the key is it may be less accurate, but again, simpler, faster, right? And so we could apply this problem to look around the world and see what's going on. And so this is sort of the representation of that. It's sort of the, in chemical engineering, a CSTR, a well-mixed reactor. Okay, so we put this together, and it turns out that it doesn't do too bad of a job. So I'm not going to show any of the equations. They're in a paper. We can go look at that. But what we have in this plot is the specific energy demand, so megajoules for every kilogram of carbon dioxide captured. We just saw that number in the slides that Evelyn showed. And then down here we have productivity. And so this is the mass of CO2, that carbon dioxide, that can be removed per unit time per cubic meter of sorbent material. And so what we see is dots, these black dots are for a 1D model, so a more computationally expensive model. This is by Bhupesh, one of our students. And then we have our model, the 0D model with no calibration. So this is just sort of how we get it out of the box. It's not too bad. And then we add a calibration factor. So if we put a little knob in there, we can get it to fit very, very well. And this was sort of surprising because I don't think Arvind, myself, or Malta thought that this would fit so well. So we were pleased that we could see this work. So this calibration factor tries to account for the differences between 1D and 0D. And this 0D model, once it's calibrated, yields very comparable results. So the answer is yes, we can certainly build a model to do this, and Malta did that. And then the second question is, what would the optimal sorbent be? So if you actually had multiple sorbents to choose from, what would you choose if you had hourly ambient conditions? And so what we'd like to know is if the results would differ between average conditions or the conditions that are changing constantly in time. And so for that, we've done some optimization, right? And so for our objective function, we have to think about a couple things. First, we want to know how much can we put through the system, the throughput, right? We'd like to know the mass of CO2 that we recover for every cycle, right? So how much CO2 can we get in time? And we, of course, want to have a high productivity so that we can minimize the cost of our machine. You know, when we pay down the cost of the machine, we're being able to capture lots of CO2 against that. The second one is carbon removal efficiency, and we want to be looking at the amount of carbon dioxide we remove net of what we emit, right? Because if we emit more CO2 than we remove in the process, this is useless. So we also want this number to be very high, right? We want to maximize this carbon removal efficiency. And Malta had the idea that we should put this together into a metric that he's calling the net carbon removal rate, or the carbon removal rate, CRR. And so this is the product of the carbon removal efficiency and the productivity together. Okay, so that's what we set out to maximize in our optimization. And it's taking care of those trade-offs. The decision variables in this optimization, we have two integer variables. So this is going to be a mixed integer problem. We have sorbent types and steam assistant. We have adjustable cycle variables, adsorption, desorption times, desorption pressure, air inlet velocity, and if steam is used, the steam velocity. So that gives us 5 continuous variables. And we set out to do this maximization, as I said. And so we had to do this through, not the standard optimization method, we'll put it that way. So hourly changing inputs we put into the system are these two as an experiment to start, right? So if we look at these, we have ambient relative humidity and temperature, and we have a black line, right? It varies just a little bit, both of those, right? So the same average for both of these. We have this bigger sinusoidal variation, right? Maybe this is binaural in terms of temperature and relative humidity, and it's much larger, but both of those have the same average, right? So we should be able to see if they give us different results. Okay, so weather's, what we're doing here is only changing the weather and seeing if we choose a different material. And so the answer is indeed it does matter. If we use the black system, we get something called APDES, and so that's one of those chemisorbents that, that we just spoke about with little hairs essentially that are capturing CO2 untethered amines. And then we have another one, which is if we have this widely varying pattern, we see that this is a metal organic framework, NBO5. And those were the two optimal sorbents that were chosen under those conditions. So we know that different ambient conditions favor a different sorbent. So why? This isn't just something that we can't explain. Well, we know that chemisorbents and physisorbents are different, as Arvind started off by saying. Chemisorbents perform better in warm, humid conditions because they allow this synergistic absorption of both water and CO2. If we have humid air, we have more water, we have enhanced support for CO2 absorption. Physisorbents are effective in cold, dry conditions, and water, and where in this case, in these physisorbents, water and CO2 are competing, right? We saw that from the theory. So dry air has less water, reduced competition, right? And we can see that in our plots of the sorbent performance here. So if we now put real weather data in, right? Because we know that the real world does not look like a bunch of sinusoids. It's very convenient for engineering, but not in reality. So we're going to compare the weather in two places. First, Malta chose Calgary, makes sense, that's where we are. And then because I think Malta wanted a vacation out of this somehow, he chose Barbados. Okay. But seriously, why Barbados? Because the temperature, right, in this climate doesn't vary a lot. It's kind of consistent throughout the year. It's relatively humid all the time, right? And I think if anyone's been to Barbados, they would agree with me that the temperature and climate is significantly different from Calgary, right? So we have two very different sets of climate conditions and weather conditions, right? And so this is our actual Calgary, right? Somewhat depressing if we think about what the average temperature is here on this scale for time in hours, 8,760 hours. And we have our relative humidity here, right? Anyone who's come to Calgary from elsewhere is buying lots of moisturizer and a humidifier because it's very dry here, right? If we look at Barbados, and those are average conditions. If we look at Barbados, right, much warmer all the time, and much more humid all the time, right? And so we have different also average conditions there. So different time varying conditions for Calgary and Barbados and different average conditions. And so when we run the model, we get different optimal sorbents. In Calgary, we'd find we use this sorbent called CIF6, which is another metal organic framework. And Barbados, we use this APDES sorbent, right? So a physisorbent and a chemisorbent. And if we look at the average conditions, we get the same sorbents, right? So the point is, even though we have these weather conditions being very different, if we use just averages, we wouldn't see that we should pick a different material, right? So this suggests it's really important that we take account when we design these materials and systems of the actual weather conditions to which they're going to be exposed, right? And so do the results differ from those if we assume a constant average conditions? The answer is yes, right? So this has been great. We've been able to show two different important points here, right? First, that we can model a DAC with a simplified 0D model. So that means we can run this model all around the world all the time and use it to figure out what the optimal sorbent would be that's influenced by the weather. And finally, that we hope to use this going forward to actually start to look at how this system would perform and inform decision making for DAC systems. And what's next for Malta? Okay, so we're going to expand a bit on the TEA and the LCA perspective in his work. He's going to incorporate some additional sorbents, because now we have good data for that to put into the model, and include the energy system in here, because what we're finding is that if we think about the energy system and the carbon intensity of the energy that's going in, that would also lead us to operate our system perhaps a little bit differently. And we hope to produce some maps, right, of what sorbent materials would be optimal and what they would perform like across Canada. So hopefully I've done this work justice, and I'll get positive notes from Malta online. And if you would like to take a look at the paper, actually the preprint went up last week, so you can grab that QR code and take a look at what came out of it. So thank you very much.
Thank you, Sean. So I'd like to invite Navjot Sandhu. Oh, we thought no one would read the paper. In the meantime, let me introduce Navjot Sandhu. Navjot is a Solutions Development Specialist at Carbon Engineering. And Navjot, the floor is yours, and thank you so much for making the trip, and it's so good to see you doing wonderful things.
Thank you, Dr. Arvind and Sean, for having me, and to Pamela as well for inviting. Hi, everyone. My name is Navjot Sandhu. I'm with Carbon Engineering.